what is the momentum? Okay. Precisely speaking, it should be called the linear momentum. In 24, physics 24, 25, we are going to start with angular momentum. That's different. But if we can drop the linear, so when we say momentum, you should understand we usually refer to the linear momentum. So it's the definition of the linear momentum is quite straightforward. It's just the mass multiplied by the velocity. Okay? And since the velocity is a vector, so the linear momentum actually is a vector. It's also a vector. It has a direction. Okay? And of course, this is for one particle. If you have several particles, each of them has their own velocity. So you can calculate the momentum for each particle from the destination and then add them together. Okay. So if you have, let's say, two particles, m1, m2, the velocity is v1, this is v2, and then the total momentum should be p1 plus p2 equal to m v1 plus m v2. Please note here, this is a vector summation. Okay. So when you try to calculate the total momentum, you have to be careful with the vector nature of the momentum. For example, if you have two particles, m1 is equal to 1 kilogram, m2 equals to 1 kilogram, v1 equals to, say, 1 meter per second to the left, v2 equals to 1 meter per second to the right. Okay? Now let's calculate the total momentum of the system. So it should be P equals to m1 v1 plus m2 v2. Okay. So is it 1 multiplied by 1 plus 1 multiplied by 1 equals to 2? Is it right?
No, because it's in different directions.
Okay. They are in the different directions. So if we choose, like, say, positive to one of the directions, so when you calculate it, it has to be 1 times negative 1 plus 1 times 1 equals to 0. Okay. The momentum for the system, total momentum for the system is 0. In other words, the two momentum cancel each other, right? And in comparison, if you try to calculate the total kinetic energy of the system, think about the total kinetic energy of the system. It's 1/2 mv1 squared plus 1/2 mv2 squared, okay, m1, m2. So it's 1/2 1 times negative 1 squared plus 1/2 times 1 times negative positive 1 squared. If you do this calculation, you will see that because the square will get rid of the negative side. So this is 1/2, this is 1/2. You are going to get 1. So if you compare the momentum and the kinetic energy, you will see that they are quite different. The system, for the system, the momentum is 0, but energy is not 0. Because the square here will make any negative number positive. Now, there is a relationship between the force change in momentum. It can be written as this: F equals to delta P divided by delta T. Okay. So it says that the force is actually the rate of the momentum change. Okay. The force depends on how fast the momentum will change. Okay. So it's kind of related to our experience. If you have some object with a huge momentum, and if you try to stop it, okay, if you want to stop it in a very short time, that means you have to apply a large force to do that. If you just need to stop it in a long time, you can apply a smaller force to stop it. So described by this equation. Okay. In fact, this equation is equivalent to the Newton's second law, F equals to ma. The two equations are actually equivalent. This is also called the Newton's second law. Okay. And initially, when Newton wrote his book Principle, he used this form instead of this form. And in many advanced textbooks, they prefer to use this one. It's more general than this. Now, I just want to show you that the two are actually equivalent to each other. It's quite straightforward. We start from here and think about the definition of delta P. Okay, it's final momentum subtract the initial momentum. Okay, so it equals to the final. Okay, final momentum subtract the initial momentum. Let's consider the one dimension, so we don't even have to worry about the arrow here. Divided by delta T. Okay, that's the final momentum, initial momentum. By definition, this equals to mv minus mv naught divided by delta T, right? And then you factor out m, you get m multiplied by delta v. Okay, m minus v naught divided by delta T. So this v minus v naught is delta v, right? So delta v divided by delta T. And, okay, I think this is familiar with, right? You are familiar with this. This is actually the definition of the average acceleration. Okay? So this equals to ma. F equals to ma. So we start with this equation, we can get F equals to ma. Okay? So they are talking about the same thing. Now, we want to introduce another important concept called impulse. Impulse, it can be defined as the force multiplied by the time interval where the force is acting on the object. Okay? So with same force, if you act it, the action time is small, so the impulse is still small. If the action time is long, the impulse is large. Okay, so it's basically with the same force. If you just if you simply touch this object quickly, you wouldn't give it a large impulse. If you keep pushing it, you will give it a large impulse. So this is that. And the reason we want to introduce this term, okay, you can think about it in two ways. one way you can compare it with this quantity. In one dimension, the work can be written as F multiplied by T. So the impulse and the work, they are actually to consider the effect of the force from two different points of view. Okay. So for the impulse is the effect of the force accumulated along some time interval. The work is the effect of the force accumulated along some distance. Okay. So I just try to characterize the effect of the force, but from different point of view. Another thing let's consider while we introduce the impulse is that we can rewrite this equation. Okay? If we introduce this to get the so-called impulse momentum theory. From this equation, if you multiply delta t to both sides, you get F delta t equals to delta p. Okay. And this one, so we give it a name. The force multiplied by delta p, impulse. So we simply say that impulse equals to the change in the momentum. So we just want to characterize the change in the momentum. So we give it a quantity I. And this one can also be compared with the work net energy theorem, which says W net, okay, equals to delta K. Again, we are trying to characterize the process from different points of view. And in terms of problem solving, that kind of suggests us, if we know the distance, so it's easier for us to calculate work. So we may go with this line. If we know the time, then it's easier for us to calculate impulse. So we may want to go with this line. Okay. Any question here? So for the impulse, we have some application. To think about when you try to catch the frisbee, okay, I don't know if this can be worked as a frisbee. I couldn't find the frisbee. So someone would like to catch it? Okay. So, okay, it doesn't work very well because that's very light. So if you have a heavier frisbee and if it's moving very fast, okay, try to think about what action you're going to take. Remember, you're going to catch it this way. So you are going to move your arm a little bit back, right? When you catch the frisbee, you remember you have this kind of motion. You're not going to, when the frisbee comes from this direction, you're not going to do this way. Okay. You're not going to move your hand towards the frisbee. You're going to catch it like this. Okay. So we'll try through it quite fast.
You went towards the frisbee.
Okay.
You went towards the frisbee. Y'all both went towards the frisbee.
What?
Y'all both went towards the frisbee.
So you're not going to move your hand towards the frisbee. Otherwise, you will feel some pain in your hand, right? So you're going to move this way. And think about why you want to move backward.
To make the time longer, less.
So you try to make a larger contact time. If you look at this equation, okay? Not this equation. The delta P equals to impulse, which is delta F multiplied by delta T. So of course delta P is fixed, okay? It's given by the velocity, swirling velocity of the frisbee, and we finally have to stop. So it's a V initial minus 0, okay, multiplied by the mass. And then to surge from fading from catching the frisbee, you try to reduce the force. So how can you reduce the force? You need to make a larger contact time. So that's why you move your arm back, so increase the contact time, so you are going to receive a smaller force on your hand. Okay, so that's application. And another way to, another application is, okay, you can think about how to play the tennis, okay? Again, if you are not, okay, if you are a beginner, you probably just say when you board like here, just put your hand here, stop it. Okay, but if you are more experienced, you remember you have a action like this way, right? So I'm not good, but anyway, the idea is that you try to move the bat together with the ball a little for longer time, right? Why you want to do that? Okay, can you explain why do you want to? You're not just do this. You are going to do this way. Move your bat together with the ball.
This is natural motion.
Why this is natural? Beginner always do this. When the ball comes, you're not going to do this, right? So it's not because it's natural. You have to practice to get this.
Wait, why would we do that?
Yes, so I'm going to explain why. Looking at this equation in the back different direction. In this case, when you throw the bat, your force is fixed, right? It's given by how hard you throw it. And your purpose is to produce a fast-moving ball, right? So you want to make this quantity as large as possible, the change in the momentum, okay? And then, how can you achieve this? The force is fixed, okay? Someone has a larger force, someone has a smaller force, so it's basically something you cannot change it easily. So how can you do that? You increase the contact time. So the multiplication will be larger, so you are going to get the hard ball. So that's why we want to do this movement.
So you increase the contact time.
Yes. So you increase the contact time, so multiplied by the constant force, you are going to get a larger impulse. This larger impulse will make a larger change in the momentum. Okay, so the final velocity of the tennis ball will be larger. Okay, so that's the application to the tennis ball. Okay, do you have any question here?
Why was your velocity so weak? Why was your velocity so weak?
Because I don't want to hit anything there. Okay. Okay, so when you, in fact, this part, this consideration about the momentum, that they are related, all kinds of sports you are doing. So when you do this sports exercise, you can try to think about these problems. How can you use these, basically the impulse momentum theorem to get the whatever result you want? Now, so let's look the simple application about